for us to capture the electrical brain activity.
And using that electrical brain activity to fly an airplane? It is just part of the next generation of research into the human brain that is happening every day at the University of Memphis.
Signal coming out.
Dr. Robert Kozma is a mathematics professor at the U of M. In his computational neurodynamics lab at the FedEx Institute of Technology, he and his team are working to understand brain activity and also come up with ways to apply this knowledge towards medical, gaming, and military uses.
It's really the main goal is to understand better how brains work and to the benefit of the humanity.
That is, feedback goes from excitatory to inhibitory.
The potential applications are far-reaching and revolutionary.
Before the seizure occurs, as the seizure occurs.
One of the ways that brainwave research can have potential benefits is to help people who suffer from seizures.
And the readout is coming directly into.
The patient wears this device called an EEG sensor array, or EEG cap, which has 256 sensors that measure electrical activity in the brain in a process called an electroencephalogram, or EEG.
We're able to see, of course, each independent electrode, and more importantly, begin our analysis.
The EEG takes 250 measurements every second, and that data can be processed using an algorithm developed by Dr. Kozma and his team and analyzed to look for irregularities.
We're able to find significant attributes that pinpoint not only the seizure activity itself, but a prediction marker, a marker that says a seizure is about to occur within a certain time period.
As a doctoral student in computer science, Mark Myers is in charge of gathering and processing the tremendous amounts of data generated by the patients at Le Bonheur for this study.
We're able to simulate the same type of activity found.
Myers uses a sophisticated brain model called a K4 to detect the irregularities in the brains of the patients. And by being able to see when a seizure may occur, doctors can help the patient with a device called a vagus nerve stimulator. This device is implanted in the chest of the patient, and the wires attach to the vagus nerve, which goes to the brain. The device then pulsates to prevent or reduce seizure occurrences in the patient.
But the problem with the vagus nerve stimulator is that it's always on. And because of its pulsing mechanism, it's of course affecting the electrical activity of the brain, which causes many side effects.
The technology is...
Dr. Jim Wheelis is the director of the Neuroscience Institute and the Epilepsy Program at Le Bonheur.
When we were recording patients' brainwave activity, to give you an idea...
He says that by being able to predict seizures with the algorithm,
you can change the settings and reprogram it.
The team has created an on-off switch for the stimulator with the goal of being able to customize care for every patient.
The device is going on and off all the time, but we can alter how that occurs. So we can alter the strength of it, how long it stays on, how long it's off, and the goal was to try and tailor that to the given patient and their seizures. The hope was if we could do that, we could better control their seizures with the device than just having it kind of randomly go on and off and be the same for everybody.
What we anticipate is that as a person who's prone to seizure effects will not only not know that the machine is turned on, but more importantly, will never know they had a seizure because of the tuning of this system through our algorithm.
And that algorithm has other medical applications as well. Brain issues such as Parkinson's disease, dementia, schizophrenia, bipolar disease, and migraine headache sufferers are all possible recipients of help in the future using this research.
Can we use this brain-computer interface?
But one of the next areas they are working on is helping those who have artificial limbs and getting those prosthetics to respond to commands from the brain more efficiently.
What we're hoping we can do is take the same kind of computer technology, mathematics that's been applied to analyzing brain activity and use that in helping people that have difficulty with movement. And before we move, before I move my arm, before you move to write, our brain has already initiated a kind of a series of pre-movement steps to kind of coordinate that. We're totally unaware, they're subconscious. And so we're hoping if we can use the same kind of brain-computer interface to say, can we detect those pre-movements, we can use those to signal a prosthetic device to help the patient, whether it's to move an arm, or if they can't speak, to work a voice box for them, or to do other kind of activities that really are more limited in our abilities nowadays.
Another potential application for this work is developing the next generation of video games. There would be no handheld controller, just the device reading your brain waves to control the action on the screen.
A lot of people would like to play games where, you know, instead of like pushing buttons or they will just think and something will happen on the screen. Oh, I'm sure that will be, of course, very popular.
And relating to that, the Air Force is interested in the group's research to possibly use this technology to help pilots control airplanes.
can machine read what pilots think about and control the aircraft better than the pilot can do just by moving his hands.
For this research, Dr. Kozma is collaborating with Dr. Leonid Perlovsky, the principal research physicist at the Air Force Research Laboratory and a visiting scholar at Harvard University.
If we would be able to read kind of cognitive events just directly from EEG, essentially from the pilot's head, yeah, certainly, that will help a lot.
The process of convergence.
All of this work stems from the research of Dr. Walter Freeman from Cal Berkeley.
This cancellation,
His research on discovering and modeling brainwave properties has led to a host of new work along this line.
Basically, I'm asking the question of how do brains work, normal brains, because that's really the source of understanding of what can go wrong. And the focus of my work is to try and understand the nature of perception.
By using the EEG to read brainwaves, Dr. Freeman has been able to begin to understand the ways in which normal neural and mental functions can break down and how the brain processes information.
Instantaneous processing of vast amounts of information, finding that which is particularly relevant to you as an individual. So that really is, to my mind, a key expression of the problem, and that's the problem that I think I've solved.
He is the genesis of so many of our ideas that we've been able to take and run with and make into our own, so that the area of cognitive processing, he was able to elucidate through his theories of where that could be found. Additionally, he's been also instrumental in some of the very latest work in terms of brain-computer interfacing.
By that time...
And all of these researchers are a part of the Center for Large-Scale Integrated Optimization and Networks, or CLION Lab, in the FedEx Institute of Technology at the U of M. And the operation is still expanding.
We are working on really creating a laboratory here on campus, both with the hardware equipment and the human knowledge, and with the program involving undergraduate and graduate students and academic personnel.
So in the future, with help from research done at the U of M, it may just be possible to fly an airplane with your mind. For the University of Memphis, I'm Kathy Gianella, junior journalism major.